Hi, everyone. My name is Lily Dale, and I am a senior at Barrington High School in Barrington, Illinois. My project is titled Molecular Inhibitors of the Wnt beta-catenin Signaling Pathway in Endometriosis. First off, I would like to give some acknowledgments to my mentors, Mrs. Polly Foley, Eleanor Halterman, and Rishi Ray, for their immense support and guidance throughout this project. I would also like to thank my family for their encouragement throughout my experiment. First off, I would like to give some definitions for the compounds used in this experiment. So in the left column, you can see the name that I use throughout this research. In the middle column, you can see the molecular name, and then the left says the molecular formula. The purpose of this experiment is to utilize the molecular docking software Chimera to calculate the binding energy and number of hydrogen bonds formed between the known inhibitors of the Wnt beta-catenin signaling pathway and CBP, which is the CAMP response element binding protein. These values will then serve as a control for the rest of the experiment. Another purpose is to test the binding energy and number of hydrogen bonds formed between compounds with similar molecular structures to the known inhibitors, which are tested in step 1, and CBP. And then using these values and comparing them to the control, the next goal is to predict the effectiveness of each compound as an inhibitor of the Wnt beta-catenin signaling pathway in endometriosis. So the hypothesis for this experiment is that if ligands have similar molecular structures to the known inhibitors of the Wnt beta-catenin signaling pathway, they will behave similarly and effectively inhibit the pathway. So these ligands would ideally follow the same patterns of polarity, binding effectiveness, and intermolecular forces as the molecules that they are similar to. So for a review of literature, endometriosis is a chronic inflammatory disease characterized by the growth of ectopic endometrium in the peritoneal cavity. Despite affecting 5 to 10% of women of childbearing age, there are really no true viable treatment options for women who wish to remain fertile, and very little is known about the pathogenesis of endometriosis. However, one thing that is known is that the Wnt beta-catenin signaling pathway is a prominent pathway in endometriosis. This pathway can be inhibited by blocking the interaction of beta-catenin with the CAMP response element binding protein, or CBP. When this interaction is blocked, it prevents the accumulation of beta-catenin in the cytoplasm, which prevents the transcription of Wnt-activated genes, which can lead to endometriosis when transcribed, as it plays a key role in the regulation of proliferation, growth, and differentiation in endometrial disease. There are 2 known inhibitors of the pathway in endometriosis, ICG001, which we've renamed compound 1, and C82, which we've renamed compound 2. So compound 1 and compound 2 will be serving as controls for this experiment. Utilizing the UCSF molecular docking application Chimera allows us to measure the binding energy and number of hydrogen bonds formed between the protein, which in this case is CBP, and a ligand, which is either ICG001, compound 1, or C82, compound 2, or a compound that is similar in molecular structure to either one of those inhibitors, which would be compounds 3 through 10. So the variables in this experiment, the independent variables are compounds 3 through 10, which share a molecular structure to the control, either compound 1 or compound 2. So the independent variables, compounds 3, 4, 5, and 6, share a molecular structure to compound 1, and the independent variables compounds 7, 8, 9, and 10 share a molecular structure to the control compound 2. So the dependent variable in this case is the average binding energy with CBP and the average number of hydrogen bonds formed between CBP and each compound. So the materials for this experiment would be a computer with UCSF Chimera and AutoDoc Vena applications already installed. Then you would need to go onto the PubChem database and find information about each of your compounds, compounds 1 through 10, and then go onto the protein databank database to find information about the CBP protein. So a quick little procedure, you would have to first import your ligand or compounds 1 through 10 into Chimera using its SMILES string from PubChem, which you can just copy paste right from PubChem into Chimera. You then have to prepare the ligand by minimizing its structure. You then import a protein into Chimera using its PDB downloaded file and delete its residues to prepare the protein for molecular docking. Next, you would prepare the two compounds together for docking by clicking Dock Prep and following the instructions by clicking OK. Next, you would enter AutoDock Vena and input the correct binding coordinates and size for the binding site of the interaction between the protein and the ligand. Next, you would run the docking, taking note of binding energy and the number of hydrogen bonds formed between CBP and the compound you're testing. You need to repeat this 3 times for each compound, so you have a total of 3 trials for compounds 1 through 10. So the results for this experiment are based upon the idea of a high probability, a medium probability, or a minimum probability of being effective. So if a compound has a high probability of being effective, it would have a more negative binding energy and it would form more hydrogen bonds on average with CBP than its respective control. If a compound has a medium probability of being effective, it either has a more negative binding energy with CBP, or it forms more hydrogen bonds on average with CBP, but not both, than its respective control. If a compound has a minimal probability of being effective, it has both a less negative binding energy and forms less hydrogen bonds on average with CBP than its respective control. So the first 2 graphs on the top row compare compound 1 with compound 3. And as you can see, compound 1 has a more negative binding energy than compound 3, but compound 3 forms more hydrogen bonds on average than compound 1. And as you can see, the error bars in both of these graphs are not overlapping, so we are able to make a definitive conclusion that compound 3 has a medium probability of being an effective inhibitor. In the bottom row, you can see compound 1 versus compound 4. Compound 1 has a more negative binding energy than compound 4, and these error bars are not overlapping, so we know this is statistically significant. However, in the bottom right picture, the error bars are overlapping, indicating that there is not a significant statistical difference in the average number of hydrogen bonds formed with CBP in compound 1 versus compound 3. Therefore, we cannot come to a true conclusion about the effectiveness of compound 4 as an inhibitor. In the top row, you can see compound 1 versus compound 5. Compound 1 has a more negative binding energy than compound 5, but it forms less hydrogen bonds. And again, these error bars are not overlapping, so these results are statistically significant, and we can definitively say that compound 5 has a medium probability of being an effective inhibitor. In the bottom row, we can see compound 6 versus compound 1. And again, compound 1 has a more negative binding energy, yet compound 6 forms more hydrogen bonds on average. And these error bars are not overlapping, so there is a statistically significant difference in these values, and we can therefore say that compound 6 has a medium probability of being effective. Next, we switch over to the compounds that share molecular structure with the control compound 2. So in these cases, we can see that compound 2 forms both more hydrogen bonds on average with CBP and has a more negative binding energy than compound 7 or compound 8. However, in both of these cases, the error bars are overlapping in the average number of hydrogen bonds chart, which means that we cannot come to a definitive conclusion about the effectiveness of compound 7 or compound 8 as being a potential inhibitor of the pathway. Again, compound 2 has a more negative binding energy than both compound 9 and compound 10. And compound 2 formed less hydrogen bonds with compound 9, less hydrogen bonds than compound 9, but more hydrogen bonds than compound 10. In compound 9, these error bars are overlapping, so we are not able to arrive at a true conclusion about the effectiveness of compound 9. However, the error bars in both graphs for compound 10 are not overlapping, indicating that there is a statistically significant difference, and we can definitively say that compound 10 has a minimal probability of being effective. So one potential experimental error is binding site inaccuracy. So the binding site for all of these trials was set based upon that of the known inhibitor to maintain consistency. However, this might not necessarily be the correct binding site for each compound, which may result in an over or under approximation of the number of hydrogen bonds formed. Additionally, Chimera changes the order in which it looks at bonds each time, which may also result in an over or under approximation of the number of hydrogen bonds formed. In conclusion, compound 10 has a minimal probability of being effective because it formed less hydrogen bonds on average and had a less negative binding energy. Compound 3, compound 5, and compound 6 all have a medium probability of being effective because they had one or the other, either a more negative binding energy or formed more hydrogen bonds on average than their respective control. Compound 4, compound 7, compound 8, and compound 9 are inconclusive as the error bars were overlapping on their graphs, so we were not able to arrive at a statistically significant conclusion for each of these graphs. Therefore, the hypothesis is not supported by this data. The hypothesis stated that compounds with similar molecular structures will behave similarly. However, all of these compounds share a similar molecular structure to either one of the inhibitors. However, none of them have a high probability of being effective. Therefore, this hypothesis is not supported. Thank you so much for listening, and please email lilymdale@gmail.com with any questions. And additionally, I would like to point out that even though this hypothesis was proven not to be correct, this research still holds significance and can be further continued by further testing those compounds, compounds 3, 5, and 6 that have a medium probability of being effective. Further testing these compounds in silico or through computer modeling will help able to determine if these compounds have a higher probability before they are tested in vitro, if at all. So again, even though this research didn't necessarily follow the hypothesis, it still has a real-world application and can help make a difference in the treatment of endometriosis. Again, thank you so much for your time, and please email if you have any questions.